Now, this is going to be the first multiple stage video, meaning that there's going to be multiple problems that show up in this video that are of the same kind of format, if you understand what I mean. And the first part 1, is this integral. This integral was calculated by Euler first, I think, and it has a very nice result. And it uses a lot of the very commonly found functions, very nice functions indeed. Now, the first thing we're going to notice is this natural log of x. That's kind of what's bothering us here. So how about we use a function representation of this integral so that we can do some manipulations with that function and find a nice result. And for this case, I like to introduce something called the gamma function. You've probably heard of it before. Integral from 0 to infinity t to the x minus 1 e to the negative t dt. This is a very nice function. And taking the derivative with respect to x, we get gamma prime is going to be equal to integral from 0 to infinity of the partial derivative with respect to x of t to the x minus 1 e to the negative t dt. Okay, so now it's basically simple derivative rules. This is constant, so move that out. This t to the x minus 1 is it's an exponential when you're differentiating with respect to x, meaning that it's going to be like t to the x minus 1 times the natural log. And this is very nice because we see the natural log popping up and we still have this e to the negative t. All that's different from this and that is this t to the x minus 1. And that's why we want x being equal to 1. So this will be t to the 0, which is just going to be 1, which disappears, meaning that our original integral can be expressed using the derivative of the gamma function, specifically gamma prime of 1. That is a very nice thing to have handy, the gamma function. It shows up a lot of times. The next thing we're going to do is draw upon another function. So this goes away. Once again, if you can't keep up, just grab a piece of paper, do it yourself, and just see how it all works. Anyway, next is going to be the digamma function, which we'll be introducing. The digamma function of any variable s is going to be equal to the derivative with respect to x of the natural log of the gamma function. And simple derivative rules using the chain rule and stuff, we have gamma prime of s over gamma of s. Okay, now multiplying both sides by this gamma of x, we will isolate this gamma prime, and we have a nice formula that says that the gamma prime of s is going to be equal to the digamma function of s multiplied by the gamma function of s. Alright, very nice. So now we can just plug in 1 to the s's. And note that gamma of 1 is basically 1 minus 1 factorial, which is going to be 0 factorial, which is going to be 1, meaning that this is kind of irrelevant, and all we have is the digamma function evaluated at 1. Which is very nice to see the conversion of two functions. And now we'll get into some special function stuff. So the digamma function of s is going to be equal to negative the Euler-Mascheroni constant. I don't know if that's how you pronounce that, but I pronounce it that way. Plus integral from 0 to 1, 1 minus x to the s minus 1 over 1 minus x dx. Very nice. And just so I don't humiliate myself, I'm going to call this constant Mr. Euler. So there wouldn't be any confusion with Euler-Mascheroni. And the next thing we're going to do is just plug in 1. So after plugging in 1, we get this is going to be 1 minus 1, which is going to be 0. X is 0 is going to be 1. 1 minus 1 is going to be 0. Meaning that if we plug in 1, this entire integral evaluates to 0. Meaning that all you have left is this thing, which is going to be negative Mr. Euler right here. That is a very nice solution. Euler derived the solution to this integral, I think, first. There's no surprise in that, but that's a fun fact, and this is very nice first point, or first part of the problem. And after that, we'll move on to the second part. Now, looking at the second part of the problem is probably more obvious as to how you would do it. I mean, we see this x to the t over here, and that's a very big clue. So once again, we're going to follow the same footsteps as before. We're going to take a look at the gamma function. I'm not going to say everything again. You should probably remember from the last part, minus 1 is a negative t. Okay. And then following the same footsteps as before, we'll also take the derivative once again. Once again, I'm not going to show the steps anymore because, well, you kind of already know, actually. And now it's very clear what to do. You just plug in s plus 1 and there you go, there's your result. Meaning that our point 2, or part 2, is equal to the gamma prime of t plus 1. Okay, very nice. And now just erase everything. And following the same footsteps as before, once again, we continue to look at the digamma function of t. Once again, I've switched variables, so I really don't know why. dt natural log gamma t is going to be equal to the gamma prime of t over gamma of t. Meaning that from this Meaning that from here we derive the solution gamma prime of t, then we go to digamma of t, gamma of t. Once again, we've explained this in the previous part before, so you should be able to catch up on this. Okay, so the next thing is plug in t plus 1 to here and here, and this time we can't simplify this gamma of t anymore because, well, t is not equal to 1, so yeah. Okay, so now we have this is going to be equal to the digamma function of t plus 1 multiplied by gamma of t plus 1 is going to be basically t factorial. And we could just write it that way using the exclamation mark. Once again, we're going to look at the same definition of the digamma function. Digamma of t is going to be the negative Mr. Euler right here plus integral from 0 to 1, 1 minus x to the s minus 1 over 1 minus x dx. This time I used quite a different method. After we plug in t plus 1, we get this part. Digamma of t plus 1 is going to be equal to t plus 1 minus 1 is going to be t. And I thought of a new kind of way to solve this, and this includes the geometric series. So once again, what is the geometric series? Well, it says that the series n is equal to 0 to, actually let me change the variable to k to n of x to the k. This is going to be equal to 1 plus, no, I think that's minus 1 minus x to the n plus 1 over 1 minus x. Baby Gauss proved this kind kind of thing when he was like 3 years old. So very impressive of him. And now, if we just plug in n minus 1 to here, we get n minus 1 over here, and then that would be this thing right here. And this thing is exactly the integrand from before. Okay, so this is going to be equal to negative the Euler, I should be saying Mr. Euler, right? So negative Mr. Euler plus integral from 0 to 1 of the sum. This is going to be a finite sum. K is equal to 0 to, this is going to be input, it's going to be t, meaning that it's going to be t minus 1. Okay, and then this is going to be x to the k dx. And this is going to be very easy to integrate, reverse sum and series, because, I mean, reverse integral and sum, because first of all, it's a finite sum, and second of all, even if it is infinite, we are in the radius of convergence, meaning that it's pretty obvious what to do, to be fair. And this is a very easy integral, so it's yeah. Evaluate from, I think it's 0 to 1. Yeah, evaluate from 0 to 1. I don't know why I'm so confused with some of these stuff. Okay. Now comes the conversion to a very nice series. I don't know why I had to think about that. So if you plug in 0, it's just going to be 0. If you plug in 1, it's going to be 1 over k plus 1. And let's shift the index. Okay, so first of all, this reduces to 1. And then after we change k to go from 1 to t, 1 to t, this will be now the harmonic numbers. Harmonic t. Very nice, okay. And so now it's pretty easy. Just maybe switch around the order to make it look nicer. We get, this is the harmonic teeth number of the harmonic series. How would you explain it? Minus Mr. Euler right here. And this is exactly, not exactly, but this is another representation for our digamma function. I think for t being an integer, because we have this harmonic thing, and that doesn't apply to real numbers, unless you do some analysis work, I guess. Meaning that if we plug in this result, plug in for that, we get this equals to t factorial multiplied by the harmonic teeth number minus Mr. Euler right here. And that's a very nice solution to our integral, including the harmonic numbers, surprisingly. And to be honest, before I evaluated this, I had no idea that digamma function and harmonic had some very nice relations. So that is going to be part 2 of the video. And next, we're going to move on to part 3, which is going to be the most generalized integral of this kind that I have evaluated before. See you there. And we're finally here on part 3. We have a new factor on our exponential function. And our part 3 actually kind of uses part 2 actually. So remember what part 2 was. We got that the integral from 0 to infinity of x to the t, e to the negative x, natural log of x dx is going to be equal to t factorial multiplied by the harmonic teeth number minus Mr. Euler right here. Alright, so very nice. So now we have this kind of thing, and the only thing different is this S is missing. So how about we make it disappear? How about we do a substitution, and this substitution will make this S disappear? That's my train of thought when I first look at part 3 of the problem. Yeah, so what I did, I let U, okay, so I should probably use my red pen for substitutions. I let U be equal to Sx, okay? And then we have x is equal to U over S, meaning that dx is equal to du over S. And now if we substitute this thing, we find that the bounds don't change if S is greater than, if S is greater than 0, which, I mean, it definitely needs to be greater than 0, or else this thing will go to infinity and the integral will diverge. So here we're technically saying that the bounds of integration don't change at all with the with the convergence of the integral. Yeah, I did not script this, by the way. Anyway, we have integral from 0 to infinity. Once again, the bounds don't change. I've literally spent 2 minutes explaining. Plug in u over s to this. We have u to the t over s to the t. Once again, this is a constant. Move that out, whatever you like I care at all. Okay, this is going to be e to the negative u. Then we have the natural log. It's going to be u over s du. Okay, that's fun. We got another integral out of it. That's great. And the next thing we're going to do, we're going to break up this natural log, move this to the front, and then we find the gamma function appearing again in integral form after we split this natural log. So I'll see you there. I need to get a new pen first. Every single video, my pen is like, yeah, alright, I'm a head out. And this video is no different. I hope this pen will work now. Once again, like I said before, we're going to break up this natural log and move this out. This is going to be equal to 1 over s to the t times integral from 0 to infinity of u to the t, e to the negative u, natural log of u minus, technically there will be a du minus integral 0 to infinity. First of all, the natural, once again, the natural log property is natural log of u over s is going to be the natural log of u minus the natural log of s. And here the natural log of s is a constant, meaning that we can technically move that out. However, I have no space. So just keep that in mind. U to the t, e to the negative u, du, multiplied by the natural log of s. Very nice. And as you can see, this integral we have right here is exactly part 2 of the original problem. And we can just substitute this for that. And we notice that this integral right here is exactly the integral representation for t factorial. Meaning that we have a constant factor of t factorial. We can factor that out. And then we can just move things around. And technically, that would be our solution right here. Meaning that our original integral is going to be equal to, we have this t factorial, which we factored out, over. And actually, I kind of messed up here because this is supposed to be t plus 1. Yeah, because we're going to multiply by this du over s right here, and then this 1 over s times 1 over s to the t is going to be 1 over s to the t plus 1. But hopefully you stopped screaming at your screen for this mistake. Alright, s to the t plus 1 multiplied by. Okay, so this is going to be the harmonic teeth number. And just to make it look nicer, we're going to move this natural log of s to the beginning, I guess. So minus the natural log of s, finally minus Mr. Euler right here. And that basically concludes it for this video. Part 3 is very generalized, including the harmonic, natural log, the factorial, and Mr. Euler right here, which is very nice. And actually, if you plug in s is equal to 1, we get t factorial over it's going to be 1, and then the natural log of s is going to be basically 0, meaning that if we plug in 1 for s, we get our original solution right here, which I mean, we should receive the same result, even if it's a more generalized version. And anyways, that is it for this video. I hope you guys enjoyed, and yeah, I'll see you guys in the next video and the next integral. Bye.